Well, welcome back. In this video, I'm going to address a very important part of a study of rotation, and that is Newton's second law. Now you say, we've studied Newton's second law already. I know that. F equals ma. Well, that applies wonderfully to objects that are moving in a straight line, like left, right, up, down, a box along a nice flat floor. But when we have rotating objects, Newton's second law takes on a little different form. The concept is still very similar, but I'm going to show you a couple examples of how we apply Newton's second law. The first, probably simplest example you might ever see is how we push a merry-go-round to get it to spin. The second one is going to take a little longer. I'm going to show you how to analyze this Atwood's machine setup. We may have seen this already when we studied Newton's second law in linear form, and it told us how to get these masses to accelerate up or down based on how heavy they are. Well, now what we're going to do is we're going to add some significant mass onto the pulley where the string is wound around. We're going to see how that decreases the acceleration of our system. So let me start with a little drawing of this merry-go-round, kind of from a bird's eye perspective, and then we'll go to the Atwood's machine from there. So here's my picture of the person pushing on the merry-go-round. Might look like this. These are the handles there. Got some parameters. So we're going to call this pretty much the shape of a disc. Nice flat cylinder. It's got a radius r and a mass m. And it's very important when we're studying rotating objects that we know what the shape of the object is, how the mass is distributed. The fact that this is a disc is very important. So I'll show you how that comes into play. And we had a person, if you remember on the diagram, the person was pushing with a force that was nice and tangent to the merry-go-round right at the rim. So how do we apply Newton's second law? Well, let me show you the form that Newton's second law takes. And then I'll show you how it's analogous to what you know as F equals ma. Remember that in rotation, our analogous version of force is torque. This is like a rotating force, how we get something to change its rotation. It's not the same as a force, but it's always associated with a force. So that's what this is. It's torque. What is our analogy to mass? Well, it's rotational inertia. Sometimes you could think of it as rotational mass. It's not equal to mass, but it's associated with a mass. And then we have our rotational version of acceleration. This is the rate at which we change the spin of an object around some axis. Now, all three of these have to imply some rotation axis, and that rotation axis must be the same for all of them. Now, obviously, for a merry-go-round, we're going to spin it around the middle. So let's just describe what the angular acceleration for this setup here would be. Just reviewing what torque is. Torque is the force multiplied by how far that force is located from the axis of rotation times the sine of the angle that those two vectors make with each other. So if I draw in a little vector here from the axis of rotation to the location where that force is, we call that the little r vector. Notice that they meet at 90 degrees, which means we don't need the sine of the angle because the sine of 90 is already 1. So in this case, we just need the length of the little r vector, which is the actual radius of the merry-go-round, times however hard that force is, and then again times the sine of 90, which is just 1. And then in most problems, we'll have to figure out what the moment of inertia is. The moment of inertia depends on how that mass is distributed on your rotating object. I mentioned this was a disk because that means you can look up in your reference table in your textbook what the rotational inertia expression is for a disk. And what you'll find in there is 1/2 times the mass times the square of the radius. Okay, that's for a disk rotating about its center of mass. And then again we have alpha, the angular acceleration. So what's going to happen in this case is we're going to be able to cancel out one of the r's, and then I'm just going to solve for alpha, and we get 2f over mr. Now that's not all that insightful, but I do like you to see and kind of make sense of this. Does it make sense that you could get more acceleration if you were pushing this with a harder force? Does it also make sense that you would get less acceleration if either the mass or the radius of the merry-go-round were bigger? And if you've ever had to push somebody or push yourself and hop on a merry-go-round when you were younger, then you would know that all three of those things do hold true in your experience. So there's, again, a relatively simple case because we have one force that's exerting a torque, we have one object that we're trying to spin, we have nice right angles and everything. Now let's take a look at the modified Atwood's machine. I'm going to draw a diagram here. I'm going to put in some parameters, and I'm going to work this one through maybe a little more lengthy than I typically do in my videos, just because a lot of students run into trouble the first time they try to do this themselves. So I want to show you all the details. So imagine we've got these masses that are hung over via a string and wound around. And I'm going to call these 20 kilograms and 50 kilograms. Now when we did this before, we found that if we had a very light pulley, so we got the pulley that's being supported up here, and we used to just ignore the mass of the pulley. And what we found was that the acceleration of this system was due to the difference in the masses. In fact, the acceleration, I'm going to write it up here, for a light pulley, it turns out the acceleration is found from the difference in the masses divided by the sum of the masses and then multiplied by little g. So did that earlier, it gave me 4.2 meters per second squared. I just want you to keep that in mind. I'm not going to use that until the very end because I'm going to rework this, supposing that we have a mass of the pulley that is significant. In fact, I'm going to say it's equal to the total of the two hanging masses. Now let's give this another parameter. How about 0.1 meters for the radius? And that's all that we're going to need to know. So now how would this thing accelerate? Well, we're going to create a system of equations, which is actually how we started it with the light pulley as well. And those equations are, in fact, Newton's second law equations. So we would need to know all the forces acting on everything. So I'm going to draw my forces on here. One of the systems on which I can draw forces is this 50 kilogram mass here. So I'll call this the mass of my 50 kilogram weight times little g. It also has a tension due to this cable here, so Ft, and I'm going to call that R for right, because it's on the right side of my pulley. Now, if you remember doing these before, you say, wait a minute, why do we need to call that a particular tension? Because it's the same tension throughout. Well, I mentioned back at the time that we won't always have the same tension throughout a string. In this case, when we have a massive pulley that we're wound around, we actually have a different tension on one side than the other side. So let's look here. We have obviously a smaller weight over here. This would be the mass of the 20 kilogram object times little g. And then we have a tension here we're going to be calling Ft L, L for the left side. Now notice we also have an accelerating wheel. If these masses are moving and the string doesn't slip, that means that this also has to accelerate in an angular fashion. So it's going to be speeding up in a clockwise direction. Why would a disk speed up? Well, Newton's second law tells us that we get angular acceleration, or speeding up, if we have an unbalanced torque. So let's look at the torquing forces on this. Its weight cannot torque it because it's applied at the center. Its hinge here, the pin that's holding it up, it can also not torque it for the same reason. But these tension forces also are exerted up here. Remember, strings always pull, so we'll have a downward FTR there and a downward FTL, getting a little crowded here, there. Okay, that's the same tension that's on the right side both up on this guy and down on the pulley wheel. Same thing over here on the left. It pulls up on the block, but down on the pulley wheel. So there are the two torquing forces. Now I told you I'd try to demonstrate for you why we know those forces can't be identical. If they're identical, we would have just as much clockwise torque as we would have counterclockwise torque, and the disk could never accelerate. But if we know it's accelerating, then we're going to be able to see that FTR is greater than FTL, and that's exactly why it's accelerating. So now I'm going to write, I think I'll write it in green, the Newton's second law equations for all three of these. The linear equations, you're kind of familiar with those for the blocks that are moving vertically, and then the angular version, or rotational version, for the disk. So for this guy right here, you see I drew its forces on there. We know it must be accelerating downward, so I'm going to list this downward force first. And it would be M50 times G minus FTR equals its mass times its acceleration. I'm just going to call the acceleration A for now. What do we have over here? We have a similar form here, except because this one would be accelerating up, I want to list FTL first. So this would be FTL minus M20 times G equals M20 times A. It's a little sloppy there. That's the mass of the 20 kilogram object times its acceleration. Now, of course, these accelerations have to be the same. We call that an acceleration constraint because there's no way I can move the 50 kilogram object any faster than I move the 20. Now, what about this? Here's our new idea. A Newton's second law equation for the rotation of the disk. It takes the form as it did up here of torque equals I times alpha. Well, what is the torque? It's really the difference in the two torquing forces. This one that's tending to torque it in the direction it's accelerating, and this one torquing it in the opposite direction. So a torque is the force times how far that force is located from the axis of rotation, and then if necessary, times the sine of the angle in between them. Because our angles are 90 degrees between the vector pointing from the axis to the force and the force itself, that's 90 degrees. I will not include the sine of the angle. So our net torque is FTR, that's the right-hand one, times the radius of the disk, minus FTL, times the radius of the disk. And then what do we put in for I? Well, because it's a disk, we would look up on your reference table, how do you write the expression for the moment of inertia of a disk? Turns out it's 1/2 mr squared, where r is the mass of that disk. I gave you that as 70 kilograms. And then there's alpha. So let me clean this up a little bit. I'm just going to pull the r out over here on the left side. And then we have the right tension minus the left tension. We have 1/2 m for the disk, r squared. And here's an important consideration, and I hope you haven't stopped before now. I'm glad you're still watching, because we have another acceleration constraint. In addition to the two blocks having to accelerate with the same amount of acceleration, if this string is not going to slip on the pulley wheel, then for every little movement of the string, and therefore the blocks, we also rotate this disk the same amount. So that acceleration constraint says that the angular acceleration of the disk is related to the acceleration of the string going over that disk by this relationship here. I'm going to replace alpha with A divided by r, the radius of the disk. Now that A is the same as this A here and this A right here. What I just did there was eliminate one of my variables, which is wonderful. So now it's in kind of a crude form, but I want to take into account the parameters that we know and what we don't know. In fact, I think I'll circle them. So we know the masses, and we obviously know G. So in these equations, we don't know either tension, nor do we know the acceleration. So that's three different unknowns. If you look up at this equation here, we actually have the exact same three unknowns. Our two tensions here and the acceleration over here. So we have three independent equations with the same three unknowns, and therefore, in algebra now, we're to the point where we can solve this. Now, I think we're running over 15 minutes. So what I'm going to do is I'm going to stop the video. I'm going to solve each of these for ft. Substitute them up for these two ft's. That will eliminate those two unknowns. So I will have one equation with my one unknown acceleration, and then if you want to stop and do the same thing, you're certainly welcome to, but you can also trust me that I'll do the math right, and then we'll be real close to wrapping up and getting the final expression. All right, so I just did a bunch of algebra, and here's what I did, just in a nutshell. I algebrated this equation to solve for FTL. I algebrated this equation to solve for FTR, and then I wrote them both in blue so you could see where I put one in for FTR and one in for FTL, and that's what these two parts here are. Everything else really stayed the same here. And then I started doing some things like canceling. So for example, we have an R here, we have another one here, and two here. All the R's actually go away, which is kind of interesting. And so what I'm left with here now is just my masses and G and A. Obviously I know little g, and so I rearranged some things to kind of group my terms together. I did not show, because of space, I did not show myself plugging in 50 kilograms and 20 kilograms and 70 kilograms for these, but you can check my math if you want to. And when I solved for A, I got 2.8 meters per second squared. Now I want to remind you that when I didn't account for any mass of the pulley, what we had done maybe a few chapters ago, I got 4.2 meters per second squared. And I said at the beginning of the video, wouldn't it make sense that if you had to move more mass, get that big wheel rotating, that you shouldn't have as much acceleration if you're not changing the forces that you have? And that's exactly what happened here, a lot less acceleration. So now I know this was lengthy, but I think you're going to see things like this, where we have linearly moving objects up and down connected to spinning objects like this pulley wheel. They take different forms, but I think this will be a good guide for how you start things like that. So hopefully it's been a 17 or 18 minutes that was worth your time, and it gets you through some problems that you see in the future. Thanks for watching.